जी आवाज आ रही है आप लोगों को?
Yes, sir.
So in today's lecture, we will continue with the tutorials. There will be or I think one or two more tutorial lectures. We'll try to cover the 3D part, and maybe later we will try to cover the turbulent flow as well, because that is a little bit complicated. So two more tutorials, and then we will revert back to theory. Okay, so in today's lecture, we will simulate flow over circular cylinder. And we will see both. So far we have seen only steady flow in this see both steady and unsteady flow simulation. Okay, so what is the problem statement? We have a 2D circular cylinder and we want to simulate the flow over it. The is an horizontal velocity of 1 meter per second, and the density of fluid is symbolic, is 1 kg per meter cube, and the diameter of the cylinder is also 1 meter. So in order to obtain a Reynolds number of 20, we are simulating a laminar flow of Reynolds 20. So in order to get 20 value, must have the dynamic viscosity equal to 0.05. So these are the variable values. Okay, so we'll first create the geometry, and the flow domain will look like this. So here is the actual cylinder of 1 meter diameter. Very long. The along so far field, very far from the circular cylinder, so that the far field presence is not doesn't impact our wake. So normally in external flow simulations, what we do is it's normally provided in the literature or the publication papers, research publications. They normally provide a guidelines for a specific problem, that how far you should place your far field boundary so that it doesn't impact our actual flow field of interest. Okay, so in this case, we have placed it 64 diameters away from the cylinder. Okay, so here are the boundary conditions which will be specifying. We will split this far field boundary into two halves. So this left half of the boundary will prescribe an inlet velocity boundary condition of 1 meter per second, and the outlet of the boundary, the right half of this circle, will prescribe pressure outlet. On the circular cylinder itself, we'll prescribe a no slip boundary condition. Okay, so that is the first part, which will be the steady flow. So in the second part, what we'll do is that we will simulate the unsteady phenomenon. So in that case, we'll increase the Mach number a bit, but still remain in the laminar regime. So in that case, Mach number will be 120, and we have to tweak the parameters, the variables a bit. For example, in this case, we will increase, so we'll keep the velocity to decrease the velocity to 0.00833, so that we get a Mach number of 120. And we will observe we will simulate and we will try to animate the vortices produced or the von Karman vorticity. Okay, so this is the problem statement description. As before, I have recorded this tutorial. Just describe what steps are involved. So as before, you open the workbench and you prescribe and tell it that we're going to solve a 2D problem, and double click on geometry or right click and select Ansys design modeler. Select XY plane, make it a 2D view. The first thing is we want to create. So go back 10 seconds. So first we'll create the actual inner cylinder. Draw and click cylinder. Make sure that the P sign is here. Then you make the inner circle and then you draw the outer circle. Then you go to dimensions. First you draw the inner circle on the same origin for the outer circle. Click dimensions, diameter. First click on the inner circle, then click on the outer circle. Then in the details view, click on D1, make it 1 meter, and D2 will be 64 meters. Out. Okay, so next we want to create a surface for these cylinders. So go to concept, surface from sketches, click anywhere on the one of the cylinders, then apply and then generate. So it will create a surface. Next, you create a new sketch. What we want to do is that we want to, for our boundary condition prescription, I told you because the left half of the far field boundary will be inlet and the other left on the right will be the outlet. So we want to split this surface into two parts in order to prescribe the boundary conditions and to prescribe the meshing, the right shape of the meshing as well. So what we are going to do now is we're going to create a projection by drawing a vertical line. First we'll sketch a vertical line and then we'll draw a vertical line over it and then project this vertical line to the surface in order to split this circular domain into two parts. So this is something which we have done before as well, so it should be straightforward. So you first draw a sketch, make sure C is on, then you drag it down vertically, make sure V sign appears there so that it is right at the vertical axis. And you trim the unnecessary parts. Similarly, you zoom in and trim the unnecessary parts which are overlying the cylinder. So that will be your sketch. Then you need to draw a line from sketch. So click line from sketch in the concept menu. Select these two lines. Just press Control key and sketch these two lines. Select this line, apply, and generate. Next, you want to project this. So there will be two line bodies. Go to Tools, Projection, select these two new creative lines, apply, and target. For the target, select the surface, then generate. That will be it. We have created divided the surface into two parts. You want to suppress the line bodies because they will not be carried over into the next stage. The other thing which you want to do is you want to prescribe the click on surface body, then select in the details that tell the incisor is it will be a fluid domain. That is it in the geometry part. Next we will go and do the meshing. So double click on the mesh, it will start the meshing module. So again, you want to do the structured meshing. So select the two faces for structured meshing. And then you want to apply the sizing. So we have got two cylindrical surfaces and two radial lines. Okay, so first you select these cylindrical surfaces, outer and inner, and prescribe those regions will be 96, be hard. Then you select the two vertical lines, keep in 96, and behavior. The next thing you want to do is that again you want to create a biasing because you want a much refined mesh in order to capture the flow physics near the surface of the cylinder and around it. So again, we want to create a biasing here on these two vertical line spacings. Select a bias type and give it a bias vector of 460. So you can see that biasing has appeared on the upper vertical line. Similarly, you want to create a new edge sizing on the lower vertical line. So duplicate that sizing which you created for upper vertical line, and then here you select the lower vertical line. Again, the bias vector be the second type because it's opposite of that. Okay, so in some cases you might get opposite of what I have got here. So some students have reported me that we are not getting the true or desired biasing type. So in that case, you want to try this bias types. So sometimes the geometry orientation is not what I have got. So sometimes this direction of this line is in the opposite direction. So in that case, we simply want to try various bias types in this menu in order to get the right or desired bias type. So it's not always the same which I have bought. Could be change it from here. So you don't have to follow what I bias type. You can try second bias type, third. Okay, so once you have done the sizing, you create the mesh. You can see we have got a very good structured mesh, which is much more finer near the cylinder, and in the far field as we move away from the cylinder it is much more sharp. So it's a dual benefit because it's saves the computational cost as well. We don't want to have a much refined uh, mesh here in all, and secondly it gives a very good resolution solution near the cylinder. So biasing is beneficial. Okay, next what you want to do is you want to create the boundary names. So select the left half and name it as far field 1. We'll select the right half of the boundary and name it as far field 2. That will be the outlet boundary. And then you can also select by for selecting the surface icon, and then you can select the surfaces and name them as flow domain. Make sure you select both of the surfaces because the surface has been split. Because our meshing will be done at this stage. To update the mesh, right click on mesh and update. And then you launch Fluent. You can click on mesh display. In general, mesh display here, and make sure that everything is imported in as desired. So here we want to first go to models and make sure that we select the laminar. Energy is off because we're not going flexible or supersonic. Then you go to materials, fluid here, and the density is 1, viscosity is 0.5, I guess, 0.5. Click change, create. Okay, that's it. And then we're going to do the boundary condition prescription. The cylindrical wall is wall. Far field 1 is our inlet. So this will be velocity inlet. We'll prescribe velocity over here. Select the specification of the components. Value of x velocity of similarly our field 2 is our outlet, so this is pressure outlet. You don't have to do anything over here. Make sure that the gate pressure remains 0 as our reference pressure is atmospheric pressure. Okay, in the reference values which will be used for calculating various coefficients, prescribed density equal 1. And then you go to solution controls. This is okay. Go to monitors and residuals and decrease it to 1 into 10 to the power minus 6. You can also create, if you want to look at the drag value over the cylinder, you want to create a report definition first as well. So tell the solver that give me the values of drag coefficient as well. We will create a report definition later in the unstudy flow as well. We have done this thing before, so here it is. Yeah. So monitors. Create a new drag report. Name it as CD. Select cylindrical wall. You can select this menu. You can check these 3 as well. So then you go to initialization, standard initialization. The type values here are the from far field. Basically, it will make the x velocity as 1. And then you click on initialize and the calculation. Give it any big number and then hit calculate. It will take around about 2 for an calculation is So after the solution, processing to see various variables and results. So we do close this one and we will do the post processing in CFD post. So double click on results, and as you know that CFD post, or by default it uh, converts the 2D flow into a 2D domain into a pseudo kind of 3D domain. So here the symmetry 1 and symmetry 2. Just analyze your results on either symmetry 1 or symmetry 2. Okay, so first we're going to see the pressure contours. So we click on this, create contours. It will be our pressure. Make sure that you type something else than pressure, because pressure is hard coded here. So pressure contour. Okay, and variable is pressure, range is global, and location is symmetry. You can convert this view into a 2D view by clicking on Z. You see the XY plane. Number of contours, you can change it to big number, 51, so it will display the pressure contours. Okay, so what do we see here? So we see there, we see that across the x-axis on the right half and the lower half, there is a symmetry in the pressure values. Okay. So net force in vertical direction is basically 0 because the pressure forces are cancelling out. But in the horizontal direction, you see across, if you see on the front end, we have a higher pressure region, and on the lower end, we have a lower pressure region. So net force in the due to this difference in pressure will be in the right direction, okay, along the x-axis. So this will push, the flow will be pushing the cylinder in the right direction. So that will, as you know, result into the creation of what we call the form drag due to the pressure difference on the front and back. So this is one type of force this cylinder will be encountering, and second one is of course the viscous drag due to viscosity effect over the wall surface of the cylinder. And you can duplicate it in order to draw the velocity contours. Duplicate, name it as velocity contours. Deselect the pressure contours. I messed up the names here, but you want to select the. Anyways, I've clicked the names, but it's okay. So if you see at the velocity contour values, So a little bit higher velocity on the upper surfaces and almost kind of zero velocity because we will have a stagnation point here. And the back of this, in the wake and in the light at the back of the cylinder, we have a very low velocity region. We'll see later it will be a separation region. You can also analyze the velocity and pressure contours side by side in order to explain the physics more clearly. You can go to here and split the views. We did this before. I'm just skipping that. Make sure that you have this icon, click the lock icon, so that anything you make changes the view, changes to both of this. So what I've done is I have deselected this icon, selected this icon. Okay, so by selecting this icon, anything you do with the any of the views will be copied by the other view as well. So in the second view, first in this view you select a different contour, and in this view select a different contour. So you can just try this out at yourself. Okay, so if I zoom in, what do I see? So these are the velocity contours and these are the pressure contours. So there is a correlation, but there is another observation as well. So I'll just describe that. So if you see here, where the velocity is low, the pressure is higher, and where the pressure is higher, the velocity is lower. But right at the back, both the pressure and the velocity are lower. So you might be thinking in your mind, okay, uh, velocity is higher, pressure should be lower, but that is only applicable if we are solving for Bernoulli equation. Okay? And Bernoulli equation holds for inviscid flows, but here and non-separated flows. So here we are simulating viscous flows. So the Bernoulli is no longer applicable. So here you can see that this viscosity effect and pressure distribution being asymmetric, we will have this kind of phenomenon. Okay, so you shift back to a single view, and then you might be interested in drawing streamlines. See how the streamlines look like. So you click on streamlines icon right next to the contours icon, and you select. Okay, so first you want to see and observe the particle paths over here. So I go back 10 seconds. So what do? Click on these streamlines and name it as streamlines 1. And here you tell it to start from far field 1. Okay, and the number of points you can prescribe. And then you click on preview seed points so that you can see from where the streamlines will be emanating. Basically, it shows you the particle paths, but you know that for steady flow, the particle path lines and streamlines are same. So you can just visualize the streamline patterns. So every 1 points preview seed points. If you'll see here, click on apply. Go back 10 seconds again. So once you click preview seed points, it will highlight the points on the boundary from where the streamlines will be emanating. You click on apply and then it will show the streamlines. If you zoom in around the cylinder, you will see that the streamlines are going. There it will show you by color, shows you the intensity of the city. You can increase the number of points in order to make more streamlines with this. Increase it to 100. Okay, so what we are really interested in is looking very close, drawing streamlines very close to this cylinder. So instead of prescribing points at the boundary as heat, you can create a line here, okay, and prescribe the seed points there, and you can create a line here and then prescribe the seed points there in order to observe the streamlines very close to the cylinder, because there is a separation region, so we want to capture that separation region and see how does it look like. So you go to this location and then click on line, maybe line 1 or seed line 1, and I'm just putting some pre-calculated values. Put the coordinates in, increase the number of sample points, click on apply. So it will, what it will do is it will create a line over here in front of the cylinder. So deselect streamlines one or make a source out of it, and then select the, instead of half, it will select this line 1. You can see that it will show you the streamlines very closely. Okay, and you can increase the number of points further. Then you can duplicate this and create a new line at the back of the cylinder. So you wanna press 0.1 to minus 0.4. It will create a little line here. And then you ask him to start from line 2. If you zoom in, you can see a pattern emerging. It'll show you the kind of separated region. You can also change the direction to both forward and backward, and it will show you the from where these streamlines are coming from. Okay. So you can see that it's coming, streamlines are coming from here. Going around the cylinder, and some of the streamlines are just revolving it in a separation region. Okay, so this is the display of the streamlines. Next, what we want to do is that, like 10 seconds again. The next we want to do is that we're going to create a plot of pressure versus theta angle. Okay, how does the pressure varies as we move from the back of the cylinder. So theta starts from the center of the back of this cylinder to in the counterclockwise direction. Okay, so how does the pressure varies? So this is the P versus theta plot. So for that, you need to create a new expression for theta. First, you need to calculate theta and prescribe a relationship for theta in order to calculate it. So theta is basically will be cosine inverse x over the radius. So x is the axial coordinate and radius is 0.5. So what I've done is go back 10 seconds again. We click on this icon, alpha icon. So basically, so you name it as theta expression. It's an expression icon. You create a new expression. Then right click, CEL, and say A cos because you're typing this expression now. A cos, and then you type. Then you again right click, variables. You select X. X is the X coordinate. So theta is basically equal to A cos X over radius. Radius is center is 0.5, and you need to mention the units as well. So this is the right hand side, or theta equals this thing. Then you click apply, and you see that the variable is in radian. Then you click on variables. So your variable is name it as theta. So what we have done is first we have created a expression for theta and named it as theta expression. Then we have created the actual theta variable so that we could plot pressure versus theta. So theta is not there by default, so you need to create a new variable called theta and make an expression for it. So you click on X and name it as theta. And it asks you what will the expression for this. This expression will be theta expression which we just created. And then you click on apply. It will show here user defined theta. So next thing is that if you go to outline, so as I described earlier, because both CFD post shows you this kind of 3D views, it doesn't has by default a 2D view. So in order to draw this P versus theta on a cylindrical surface, which is a 2D, so you need to create a new surface, extract a surface out of it. It's by default a 3D, so you want to extract a surface out of it. So you click on location. And click on polyline. You can name it as cylinder surface or something like that. So method is boundary intersection, and intersection is with symmetry 1. Then you click on apply, so it will create a 2D surface, which is displayed here in green. Okay, so once that is done, then you need to create a chart. So click on chart icon and name it as P versus theta. Okay, so in the data series, so your location is the newly created surface, which is cylindrical surface, which you extracted. And select that, and then go to x-axis. The x-axis will be r theta, which you just calculated, and y-axis will be r pressure. Then you just click apply. It will show you the pressure variation as we move from the theta from the back to the front. Okay, so here what we have a paper, research paper to compare with. I'll upload this paper as well. So here he has drawn a similar plot for various Reynolds number, and you can see the variation of Reynolds number 20. So here is the Reynolds number 20 plot. So on the vertical axis we have pressure, and on the horizontal axis we have theta. So theta is, if you see here, it varies. So it has got an inverted axis. Is theta axis is inverted. It starts from here and then pi radians to here. It starts from 0 to pi radians. So we want to invert our axis as well in order to get a similar plot of pressure versus theta. So we go to x-axis and simply click invert axis, so that our axis starts 0 to like that. Okay, so this was for steady flow, and next you want to do is same geometry, same mesh, and then you will want to simulate the unsteady flow of it. Okay, so for that, the project which you have saved for steady flow will build upon that. So you click on this drop down menu here and select duplicate. Okay, so our geometry and mesh will remain the same, but our uh, simulation setup, we will make it unsteady. Simply double click on setup and launch the fluent. So what it's doing is basically a duplication of the same solution. So it will import the same boundary conditions and geometry and mesh. So once it's loaded, how do you perform the unsteady calculation? So far we have been keeping it as steady. So here you want to select the transient or unsteady time behavior. You simply click on transient. Okay. Other thing which is different is here in this case we have a Reynolds number of not 20, it's 120 here. So you want to decrease your viscosity from 0.05 to 0.00833 in order to make the Reynolds number equals 120. So we're just increasing the Reynolds number, so we will have a vortex shedding phenomenon. Okay, and then you can also create new report definitions. For example, here you can observe the lift. Create a new report definition, type it as CL. Make sure you select the cylinder wall in the wall zones option. Report fire, report plot, and print to console. It will display the values here. Don't hit compute, hit OK. And close it down. Then you want to initialize the solution. Click on initialize. View from far field 1 or whatever the solution there is, you can build upon that. You can calculate from the previous solution also, but in this case we have just initialized it. Okay, next thing what you want to do is, in order to get a faster convergence and to get the vortex shedding, capture vortex shedding more quickly during the solution, what I'm going to do is that I'm going to change the y velocity values in the wake or right behind the cylinder. So initially the y velocity is 0. So I'm just in this region behind the cylinder. I'm tweaking the y values to get a good guess, initial guess, and capture the vortex setting more quickly. So that is done normally by selecting this domain, and here we have this adapt menu. So in this newer version, they have hidden this region adaptation or patch, we say. So in the previous versions, there was this proper GUI for that. So in this newer versions, how to change this menu? You go to this command line console and hit enter over here. It will show you various options. Okay, and then you can type mesh or then press hit enter. It will show you again sub menus. You will go to adapt, type adapt, and then press enter. Okay. So if you press enter again, it will show you the another option, revert to this particular version. You type that in and press enter. So once you press that, you will see the menu here will change. Okay, so it has revert back to that folder GUI. So here you want to select a region where you want to prescribe a new Y value. And then it asks you to whether you want to create this region and whether you want to create a region outside of this coordinates or inside this coordinate system. So you want to select inside and shapes is quad. And then you prescribe these numbers over here, click mark, then close. Don't hit adapt, click mark. So what I've done is you will be visible from here, go to graphics, contours, velocity, and select Y component. Okay, so as a tweak, I needed to adopt that first. So once you click mark for that region, then you come back here. So rather than going straightly through the contours, first you wanna go back. Instead of going directly to the contours, come back to this initialization menu and click on this patch icon, this one. So instead of first doing this contours, click on this patch icon so that it initializes that patch. Select Y velocity, increase it to 0.2 and select this patch, not this one. Okay, and then click patch. Now you will see the contours, save and display. So what it's doing is it's showing you the initial values of the Y component. So everywhere else it's 0, but we have just tweaked this value over here in this patch in order to get a good start. Converge faster. Okay, so then you go to, okay, so this is one thing. The other thing is that in order to visualize this vortex shedding phenomena, we want to create an animation of this flow physics, flow being developing over around this and the advanced study one. So for that, you want to export this solution data to CFD post. So we will create the animation there. So you need to tell it to export some kind of data. In this case, it will be the vorticity magnitude, vorticity variable. So you double click on calculation activities. It will display this menu. Okay, then you click on create and then you select solution data export. Okay, so in the, you can name it anything. For example, here I'm just as vorticity something. And in the file type, select the CDAT for CFD post. And on the right hand side, from the variable list, select vorticity magnitude. So this will be used to display the vorticity contour or vorticity or vortices. File name you can change, and you can also change the path where this data will be stored. So you can change any, name it anything you want. So just keeping that. Okay, so I've just selected some random path inside a folder. So that's it. Close that menu and then run calculation. So here you will see that in contrast to the study flow, the run calculation menu is a bit different in case of unsteady flow. So here is basically talking in terms of uh, total time which we wanna simulate this. So here it says number of time steps and what will be the time step size. So time step size I'm prescribing zero point 0.2 seconds. Say number of time steps, you can name it a big number. So I'm keeping it as 200. You can try keeping it as 400 or 800. So what does that mean is that 200 by zero point 0.2, if you multiply these two numbers. So we are simulating this flow for, so this is in seconds. So we are simulating this flow for 200 by 2.2 will be 40. So we'll be simulating this in for 40 seconds. Okay. And in between these, for every time step, okay, we have 200 time steps. So we are telling the solver that for each time step, perform a maximum number of iterations. Okay, so here I'm prescribing 20. So if you see some abnormal behavior, you see that the convergence, well, your solution is not converging well enough, so you can increase the maximum iterations per time step. Okay, so in order just to demonstrate, I'm just keeping it 20. If you encounter some problem, you want to increase that maximum iterations. Okay, so then you hit calculate. So because we asked it to plot print to console and also display the CL graph as well, so it will also say that. And in the convergence plot, you will see that the behavior will be something like this. So in each time step, it's calculating 20 iterations. So for each time step, it starts with some values and then converge this to a certain value, and then the new time step starts. Okay, so you can see that it will be how much? So 200 time steps and then 20 iterations per time steps. So it'll be 200 into 20 for, so we are asking it to iterate like 4,000 iterations. There is a condition here saying reversed flow on 96 phases. So something, this is something which you don't want to have. It's just, but this thing is for just learning purpose, demonstration purposes. So I'm just neglecting that. Okay, so it will take some time to complete these 4,000 iterations. So I'm just skipping this and forwarding it. Okay, so once the calculation is complete, then you can either close it or minimize it. Okay. And then there is another way to launch CFD post because here we want to import a saved file. Okay. So rather than importing a solution from here, which might be problematic, so to be on the safe side, you can launch CFD post in isolation as well. So if you go to in the left menu, click on expand the component system menu. Okay, and then you scroll down and select results. this thing results. So double click on that, it will show a separated CFD post. So double click on results and launch CFD post. I go back 10 seconds. Okay, once it's opened, then you click on this icon, load case. Okay. So here you want to give the path where you saved while exporting your solution. Selected some folder and a path. Just give that path. So go to that path. Desktop, just going to that path. Normally answers it's a very high number of folders and subfolders. Okay, so here is that. So for 200 time steps, it has created, it has saved the solution into this directory. So what you want to do is you want to scroll down and select the first case or the first step solution. Okay, so I'm just scroll down and make sure you select this 001 dot case. So there'll be something here, but make sure that it has got 001 dot case. Just click open. Keep the other options in. Just click OK. So next you click on this clock icon, which says time step selector. And here you want to select the first time step. Click apply and keep this window time step selector open. So you can visualize the opacity contours, this solution, create a new contour. Variable is vorticity, location is symmetry. Okay, range is user specified in order to show it clearly. So select this range 0.01 and to increase the number of contours to some high value and select apply and change the view to XY plane. So if you zoom in, so this is the view at the start of this where the time is just 0.2 seconds. Okay, so it has started the flow is the first time step. This is how the vorticity looks like at first time step. Later we'll see how the vorticity looks like at the later time steps or the last time step. Okay, then I'll go back 10 seconds. Then you click on this movie icon, animation icon. Here you want to create the animation. So you select keyframe animation and then new keyframe number 1. And in the number of frames, you can synchronize it with the number of time steps. So You've got 200 time steps. So whatever the time steps you have got, just synchronize the number of frames so that it shows you the variation with of the vorticity with the time step. So animation is basically what? Animation is just the variation of a vorticity at each time step. Okay, so we are displaying it as a number of frames. Okay, so you want to create a total number of frames equal to the time step. It will show you the variation in the form of animation at each time step. Okay, so then you go scroll down and select the last time step and you click apply. And you can just visualize that at the 200th time step, which is 40 seconds, you can see the vortex is being shown. So what you want to do is, so you click new again and then keyframe number to make it will automatically say it's 202. Keep it as 10. Then you click on this icon over here and you want to save this movie or animation to location somewhere on your PC. So give it that path, click on save movie, and then save it to some convenient location. And then just press this play icon. Okay, so now it will show you the variation of this vorticity magnitude at each time step. Okay. Because the number of frames is same as the time steps, so basically you are viewing the vorticity values at each time step in the form of animation. Okay, so I'm just fast forwarding it. At the same time, it's also saving it as a movie. So once this whole playback is completed, just ignore this. Okay, then you can just minimize it and go to the location where you have saved that movie. Then you can play that, so it will be much faster. Okay. So here you can see the animation of this. So one thing which I want to tell is that now because there is a pressure fluctuation in the vertical direction, so there will be some CL values. And you wanna go back to this CL plot, which it was showing while iterating, and see the variation of that CL as the flow develops. Okay, so here's a display of how we can simulate an unsteady flow and also create an animation out of it. Okay, any questions?